All right. All right, so I'm Gabe, and I'm going to talk about phase mixing and turbulence and gyrokinetics. I want to highlight collaborators here because I'm going to talk about a lot of results that we have, and there's a lot of people who have been involved with that, and especially Tomo Tatsunu has done all the simulation results I'll be showing. All right, so I wanted to just continue kind of some of the discussion this morning about this approach to gyrokinetics. There's a certain context in which we're studying this problem. It's a conceptual kind of framework, and that is the idea of separation of scales and separation of fluctuations from the mean. And so you've all heard about this. So the multi-scale gyrokinetics, to my knowledge, really kind of program got initiated there, and it's had some progress over the years. And tomorrow, Ian's going to speak about current state of affairs with that.
Sorry.
Yes.
I will reveal my really true ignorance here. What are you exactly attributing to Sagama here in 96?
Transport time scale separation. The idea you can ensemble average your equations and get equations for the mean quantities and for the fluctuating quantities and separate them all out. That kind of framework for approaching gyrokinetics is a theory of fluctuations interacting with mean quantities.
Yeah. There was a cryptic one-liner in the Freeman and Chen paper that says that this could be done, but to the best of our knowledge, this is where it was done.
So fluctuations, just on a kind of conceptual level, we split up distribution function and quantities into fluctuating bits and equilibrium bits. These have gradients in them, drive instabilities, and that creates an injection of some kind of energy into the system. And it's important that we kind of get it straight from the outset what the energies of the fluctuations are, what we think are the important quantities to look at. And we've all been hearing about the free energy or the entropy. And I'm sorry, there's a little bit of confusion in notation here, but this is like the entropy times T naught, so it's call it the free energy. And then there's another quantity, I think, which is of interest. And as Alex has been mentioning, this is technically an invariant of only of the 2D system. But I'd like to kind of promote that we should pay attention to this in this quantity in three-dimensional systems as well. So that'll be kind of a theme of the talk. This is another quantity to pay attention to. And just this brief historical note, of course, the importance of that quantity, we heard all about it in the last talk, but this quantity will grow without bound if you don't have dissipation in the system. So this has been known and articulated in 1994 by John, that in order to resolve this problem, you need dissipation in the system. Actually, this E quantity that we'll be talking about, I'm not really defining it specifically here, it can be found in part of the energy invariant, the exact energy invariant in Dubin and Chromis as well.
That's why you're in charge of this group. It's come back to haunt you.
Yes, so there you go. So that's just the kind of conceptual framework. Why I'd be interested in this question? So this is me sort of trying to address the challenge from John about what are the reasons that we should be interested in thinking of gyrokinetic dynamics as turbulence, in this turbulence framework, whereby some energies are injected and cascade through scales and dissipate, this kind of framework. Well, on a very practical level, with simulations, we need to know about resolution, and it would be nice to have firm kind of theoretical basis for choosing a resolution, knowing where the dissipation scale is, knowing what channels of phase mixing are active and where the free energy will flow will help us address this problem. And studying this problem in simplified cases can give us very simple, exact analytic kind of solutions to problems, which all codes should be able to agree, and these would be nonlinear kind of solutions. So, going beyond, looking for a matching of turbulent fluxes for a specific, cyclone base case, we can think about problems that will give us reliable spectra and K and dissipation scale and so forth, these kinds of things. Fusion physics, this is more on the speculative level. What kind of damping mechanisms, in particular nonlinear or linear damping mechanisms, exist? We'd like to know what causes saturation of turbulence, and maybe there are novel mechanisms, and I'll hint about something like that later on in the talk, that can damp turbulence. How can small scales interact with large scales? Again, about the energy flows. Local, non-local interactions. It's kind of on the same. And then we've heard about zonal flows. We're interested if zonal flows are generated by inverse cascade process or not by inverse cascade process, and what are the important energy quantities associated with the zonal flows, which is the discussion that's just been going on. If you were here for the first week, Bill Dorlin presented some simulations, which is work with Kate Despan, about gyrofluid simulations. And they've essentially added in some term which takes into account a nonlinear phase mixing process due to zonal flows. He had this kind of intuition that this process is important, and this is exactly the kind of intuition that will be useful in building some simple physical models to create, drastically improved computational models, so we can scan across parameter ranges and so forth. And this is something that he talked about. Also, the issue of developing subgrid scale models. There's a group in Brussels. Danielle Karate is working on developing subgrid models to simulate using Gene, and this is a possible way of modeling small scale interactions on large scales, and we need to understand how those interactions happen to develop these models. All right, so that's kind of the big motivational slide.
Well, will you mention?
Yeah.
Oh, sorry. Here, go ahead. No, let's do the next one. So
The next
going to
one.
ask you what you're going to mention.
This is just an outline of the talk. So that's.
Are you going to ever mention some grid scale modeling again in the
No,
class?
not really. Well, I'll mention it at the end because I have some results that they forwarded along to me from their simulations, and they're interpreting these results in terms of this kind of thing. So we can speak about that. Yeah.
And I think the subgrid scale modeling of the V-perp space might raise its head again at some point during these 2 weeks because of Bill's pursuits of ultimate gyrofluid closure.
So I'm going to make a few comments about phase mixing, different kinds of phase mixing, and then I'm going to focus on 2D gyrokinetics, and I'm going to make this provocative statement, which some people might dislike. It is kind of treated as the Navier-Stokes equation for magnetized plasma turbulence. I'll explain why I would say something like that in a minute.
It's now officially accepted the Journal of Fluid Dynamics, so it's being printed on vellum as we speak, right? So everything's fine.
I didn't say that in that article. And then I'll talk about a review of some results with perpendicular phase mixing cascade, the entropy cascade, through a different channel than Watanabe-san was talking about, the perpendicular nonlinear phase mixing channel, and some sort of new results that I haven't really talked about in detail before. And then we'll go to those results coming out of Brussels.
It's interesting that in your general motivations, you didn't mention things like solar wind or other applications that are non-fusion.
Yeah.
Even though they seem to be very exciting.
Right. So I'm intentionally sort of focusing on the tokamak problem. And I think that the idea that turbulence is applicable to solar wind and that, not the inertial range and cascades and so forth is not very controversial. So I thought that it'd be good to focus on this case where maybe there's some resistance. All right, so just simple phase mixing. You've seen this kind of thing before. So parallel phase mixing, which is related to linear Landau damping. We have this intuition of if you set up a potential or distribution function, here's your z coordinate, and this is the v parallel dot grad on f term, is going to create parallel phase mixing, and that's due to just the free streaming of the particles, the parallel direction. So those particles move at different velocities, and that creates the shearing of the formation here. And you get structure, and there's this just general intuition that this kind of damps out the potential. The only rigorous kind of thing you can say in the turbulent state is that this process is not going to conserve that E quantity that I was talking about before. It's not. There's no statement that it's going to be always damping, or it couldn't as well drive this term. But this is our kind of intuition about how this term works. Then you also have instability drives which work on phase mixing, and this is just sort of a Cowley-style diagram where you have a background gradient and flow of cold plasma reinforcing potential wells, pressure minima, and causing an instability, a feedback mechanism. So this actually doesn't conserve free energy or the E quantity, the electrostatic invariant. So from that perspective, when we talk about the W quantity as being somehow an invariant of the equations, well, of course, when we have non-trivial geometry and gradients and instability drives, it's not an invariant. There's an injection, and everyone knows this. But I just wanted to point out that in a sense, these two quantities, the electrostatic quantity and the free energy, are more on equal terms than perhaps we'd like to think. Okay, so let's talk about this other phase mixing process, which is something we've been studying kind of intensely for a while, which is a nonlinear phase mixing process. I haven't put the gyrokinetic equation up, and I'm just sort of trying to work on physical grounds in the beginning here. But the idea is essentially that in gyrokinetics, particles sense the fields, like the potential, in this average sense, because they're rapidly undergoing Larmor motion, and so they perceive the field in an average sense that's dependent on the size of the Larmor radius of the particle, which is proportional to the perpendicular velocity. So this has also a natural way of phase mixing the particles, and maybe you've seen this before. I've shown this many times. I have a movie of this process, and it's not going to work. That's fine. It's the only movie, so that's all right. But these particles will move along different trajectories. Small Larmor radius will follow the potential closely because they sense the potential locally, and big ones will seem to move along different paths. That's that phase mixing process. And this induces structure in the distribution function in a very similar way as the ones as a linear phase mixing process, whereby the spatial structure is sort of imprinted on the velocity space. So the correlation, the structure induced in velocity space is about the same scale as the variation of the potential that it's sensing. All right. So 2D gyrokinetics. We're going to take this as our minimal model, and here's the equation, and this is the electrostatic potential, which is solved through quasi-neutrality, the standard bit, and there's collisional dissipation. And the physics of this equation is essentially just the physics that I was talking about in the previous slide. That's kind of all that's happening. And then there's collisional dissipation as well. So the point I wanted to make in calling this a minimal model, I've sort of already made it at this point, which is that this contains the nonlinearity. The nonlinear structure of the equation is all right here, and it's sort of like the Navier-Stokes equation. We know we can put it on a sphere, or put it or take a cylinder and spin it and impose geometrical considerations, or give mean scale flows. But really, there's a basic equation that we want to understand before we go in that direction, which is how does the turbulence act? What are the properties of the turbulence that are not dependent on the box that you put it into? And so I think this is really a good equation to study for that kind of approach. And as far as the parallel term, the v-parallel linear phase mixing term, even in a tokamak, it's possible that this scale is determined by geometrical considerations. It's not really known. I think this is an open question. And so in that sense, this is also sort of a feature of the box you're putting the turbulence in. So in summary, there's a simple equation that we're going to focus on. And there's this generalized free energy, or the entropy. Let's not get into the detailed definitions of it, but it's like looks like an entropy. It's a square of the distribution function over F naught and integrated over phase space. This is a conserved quantity. We found that a good way to look at the velocity structure that's generated by this equation is via a Hankel transform. And this is really just inspired by the fact that all these the Bessel functions that come out of these averages are right there. And you integrate over velocity, that's essentially a Hankel transform. So the quasi-neutrality is really just a statement that the potential is due to structure in the distribution function where the magnitude of the Hankel wave number is equal to the magnitude of the k vector. Does that make sense? So that means in Kp space, you can take the free energy and sort of divide it up into its density over Kp space, and right along this diagonal here is where the potential is coming from, that contribution there.
Gabe?
Yes?
This is sounding very much like the case Van analysis, where you have some singular distribution and then some decomposition.
Okay.
Is this something that you're going to use?
No, I won't talk about that, but that sounds interesting. I don't really know.
I didn't quite understand that. Could you?
Well, if you go back to the equations that you have G representing the distribution function, you have phi, and then you have some operator which essentially the fact that K must only be equal to P looks like a delta function, so it's a singular distribution in the entire K space. There's only a very specific, for each K there is a specific P.
So let me explain that. There's no assumption that the free energy lies along this diagonal. The free energy occupies this entire space. So G has got a structure on all scales in velocity space given to it, and in real space, I mean, it's got turbulent structure in it. This is just a simple mathematical statement that when you look at this expression in K space, this gyro average is turns into a J naught, and it's integral of G J naught. That's a Hankel transform. That's all it is. So it's just a natural space to look at the problem in. So here's some simulation results from Tomo Tatsuno. We'll look at the, now let's specialize to the sublarmor for energy cascade, because this is sort of where we've been focusing on understanding this mechanism. So we'll start with an initial condition at K rho. This is normalized to the ion armor radius. A little bit greater than 1. We'll see how it diffuses in Kp space. There's P space, again, the wave number for the velocity space, and there's K space for the position space. Oh, this is also a movie as well. That's unfortunate. Sort of works not in full screen. Okay, so the features to notice, it sort of propagates in this direction to high K and high P. It's diffuse. It also there's also diffusion off the diagonal there. But actually, the peak is along K equals P, which is interesting. We'll talk about that. Ooh, sorry. Can I start the slideshow from here? I should know a short key. Yeah. And so we've worked out these inertial range spectra for this cascade. So these are the K spectra, which means we integrate over P space this way. Integrate over P space, and these nice power law spectra, and these were originally derived by Steve and Alex, I think, based on the hypothesis they came up with at Lake Arrowhead. Is that right?
Yes, it was a very, very boring place, so we actually got some time to work. The food was not denied.
And so
that implies that nothing's going to happen here.
There you are. Well, food at Wolfson Court is conducted to
Wow.
scholarly research.
Go ahead.
all right. So these are really nice asymptotic demonstrations of this inertial range that exists. And also we have predictions for the shape of this P spectrum, which is not up anymore. But if you take slices and look at the power law dependence in P space at constant K, slice across, you can see a nice power law spectrum there. So all those features are well described by this sort of inertial range cascade theory as well. And also, we've done diagnostics with the transfer function. And to do this, basically, you just take your fields, your distribution function, your potential, and you filter it into shells of different magnitudes in K. And then you compute the nonlinear interaction between those K shells, and you can get a sense of where the energy, what K shells are contributing to the energy flow. So this is sort of the K from and the K to, Q and K. And we've looked at K space and also P space in creating out K. And in both spaces, the transfer is highly local. So these figures are sort of, they've got a double the information. This is redundant. So there's an anti-symmetry here. So really you just have to look at one side or the other. This is a forward cascade, a local forward cascade from 1 to 2, from 2 to 4. You know, this is how you read this diagram. Local cascade in K space and P space. This is also a nice confirmation that this turbulence is behaving in a way that that's similar to fluid turbulence. Okay, so let's talk about something else we're observing, a dual cascade. And so this energy invariant. It's electrostatic energy, if you like to call it. I don't think there's been really a good word name for it that's come up yet. But this is something like the potential squarity of these operators as well. It's the ratio of the temperatures, Ti over Te. But this is essentially the energy associated with the potential. And this is also invariant. And there's a special relationship between the spectral density of this energy and the free energy. And this comes directly from that expression where you can express the potential in terms of the distribution function. This is it right here. This is the constraint on these two spectral densities. So the energy at some wave number k perp, we'll just look at an isotropic way, this is just a magnitude k perp, is equal to, with some constant proportionality in the front here, the free energy at k and k divided by k. So there's an extra factor of k in this expression. And this is precisely the setup for a kind of inverse cascade. So the transfer of this is going to affect the transfer of that. That's how you get a dual cascade. Two invariants that are mutually constraining in k space. But this is a little bit different than the traditional fluid inverse cascade because the constraint only exists along this diagonal. So there's a big freedom here to choose different kinds of scenarios and see how the turbulence will develop. So I'll describe that in a second. But we can understand this in terms of sort of elementary 3-scale transitions, and then you can think of more complicated interactions as being a composition of these kind of elementary transitions. And this is essentially what Fjortoft did in his 1953 paper for fluid turbulence, two-dimensional incompressible fluid turbulence. So the first case we consider is transfer just along the diagonal, 3 components along the diagonal. And this is exactly the case of 2D fluid turbulence. In order to maintain balance, if energy is transferred forward, you must also transfer some backward, and that gives you this dual cascade. As you consider bigger and bigger scale differences, most of this is going to be your energy, is going to correspond to energy, and most of this is going to correspond to free energy. So that gives you a forward cascade of free energy and inverse cascade of electrostatic energy. This transition is similar. When you transfer free energy off of the diagonal, there's a deficit of electrostatic energy. In order to make up for that deficit, you also have to transfer backwards. This is also sort of an inverse cascade mechanism. Whereas transfers among non-diagonal components really are not constrained because it doesn't, there's nothing that this expression says about those kinds of transfers. So let's look at this again. This is another simulation by Tomo. And here we start with a little bit of free energy, highly peaked along the diagonal. It's at k equals p essentially, concentrated right there. And there you see an inverse cascade, a very strong inverse cascade of the energy along the diagonal, which is sort of what we expect from this mechanism. The features that are interesting of this inverse cascade is it's highly peaked in the diagonal, whereas in the forward cascade, the diffusion was such that the spectrum fell off as a power law for k not equal to p. In the inverse cascade range, the free energy is highly concentrated along this diagonal, which corresponds, as we've been saying, to inverse cascade of electrostatic energy. So that's sort of the description of what's happening there. I think that's the last movie, so we're good from here on.
Gabe, why is it that the spectrum there's discontinuity at k perp of 2 or something?
Oh, you mean the sort of...
Yeah, it seemed like it was inverse cascading kind of symmetric about this k equals p line. Then
until it gets to large scales.
Until it gets to large scales, that just died. Right.
So that particular mechanism, inverse cascade, is really active at the sub-Larmor scales. We don't really know exactly how to extend it to the Larmor scales and the larger scales yet. So that's sort of outside of the range of applicability of the theory. So there's more ways that this can happen. As I was hinting at, this is not a fluid inverse cascade or not a fluid dual cascade. So there are different scenarios that will give you different behavior. One, which is this is not actually the one we've just seen, but this case corresponds to free energy being localized at some scale, but sort of distributed off the diagonal as well. So there's a ratio of W to E, which is larger than if it were concentrated on the diagonal. And for this, we expect the cascade to proceed locally. And that's what we see in the simulations. What you saw in the movie I just showed was something which is highly localized along the diagonal. And here we observe and expect the inverse cascade to occur non-locally. And the reason for this is essentially that this energy as it diffuses in K and P space is going to consist mainly of these kinds of interactions, which are more strongly driving the inverse cascade. Whereas if you have an equal amount of, if you have energy broadly distributed around K equals P, the diffusion in KP space is going to be consistent of interactions like this and this and this. It's going to be more of a broader distribution of interactions. So that's a non-local inverse cascade mechanism, which is observed in the simulations, which you see. Not sure, I don't have the movie. I have it somewhere on my hard drive. Probably should have put it. But if you look at the K spectrum, you see essentially a peak shooting up in the very beginning of the simulation. And also, if you look at the transfer spectrum, you see the corresponding non-local interaction. So that's the sort of physical basis for that. There's something else which you can do, which sort of turns the whole argument on its head, and that corresponds to a somewhat seemingly unphysical kind of situation where there's very little free energy along the diagonal, and most of it's concentrated off diagonal. And this is sort of, in a sense, this is what's the word? It's a difficult limit because the size of the potential, which gives rise to the dynamics of the system, really diminishes as you take this limit. But we can imagine that there's a seed potential, and further, we could also consider that there's some ambient turbulence, and we're just injecting free energy in this manner. So I think this is a physical kind of scenario, in fact. And what this gives rise to is a dual forward cascade, because as this free energy cascades forward, it's inevitably diffuses forward in a sort of random way. It's going to start occupying the diagonal. In order to do that and conserve energy, there must be a forced transfer of energy from the large scale. So it's sort of a forward cascade that's a dual forward cascade that's constrained in this sense. It's not. You can think of two independent fields that are turbulent and interacting, and they would both forward cascade without any constraint. But this is a slightly different kind of dual forward cascade where the transfer is actually constrained, it's forced. And this could be some kind of novel mechanism of damping for the larger scales. We could call this sub-Larmor damping. So this is kind of a interesting case. If you are able somehow to drive zero density fluctuations in the ions in a fusion plasma, you could possibly damp out large scale fluctuations in the potential. I've gained a little confidence in this idea when Michael Barnes told me about a simulation that he'd been doing where he excited random fluctuations in the distribution function for some a jet case or something. And actually, the way GS2 initializes things, these fluctuations would correspond to zero density fluctuations. So this would correspond exactly to this case where you have most of the free energy is being injected off diagonal. And he observed a reduction in the heat transport under those circumstances. That's interesting, and I think that, I mean, it's maybe speculative at this point, but I think that for me this is clearly the exact setup you would like to see. And although it's a simulation, you know, if anyone can think of a way to drive sublarmor fluctuations, zero density fluctuations or small density fluctuations, then this could be an interesting way to damp out the energy containing scales. How am I doing on time here? I was going to talk a little bit about adding in some linear phase mixing to this picture. So we can look at parallel phase mixing at the sublarmor scales and try to tackle it by a number of different approaches. You can assume some kind of that there's some kind of single helicity where the K parallel matches K perp in the sense of Watanabe-san, or you could consider some critical balance where the parallel time scales balance the perpendicular turnover rate. The critical balance returns the conclusion this is probably weak at the sublarmor scales. It doesn't say that it's weak at the energy containing scales, so it's still probably very important. But in any case, if we're going to add it to the sublarmor calculation, it seems like it might be weak. But it's a very difficult problem to kind of tackle rigorously numerically because it requires an additional dimension. We're already pushing limits to resolve this perpendicular cascade. So an idea would be to include perpendicular phase mixing via a magnetic drift term. So we don't have to do a 3D simulation, but we can stay in 2D and have a linear phase mixing process. So I had a poster on this, and it's very kind of preliminary idea, but I guess I could just talk about sort of the general idea of it, rather than to get on the details. But the basic idea is that as the perpendicular cascade advances, the linear damping term gets stronger and stronger relative to the nonlinear term, and there's a certain point where it crosses over, and at that point we don't know what the scaling is. But if you assume that the scaling is the same as the perpendicular cascade scaling that we've had, then this term just starts to dominate the linear term. So this gives rise to fast kind of wave dynamics. And again, this term is a v perp that grad on the distribution function. So if you integrate it over a box, it's going to conserve the entropy. So it's sort of like it's basically you have wave-like dynamics in velocity space, but there's sort of a shearing in velocity space as well. So there's a mixing that's happening, and this gives rise to a drift velocity which depends on velocity, on the velocity of the perpendicular velocity of the particles. So the way to, I think, to tackle this problem is to start with this kind of ansatz, this weak turbulence ansatz, that on the fast time scale this behaves like a wave process, and the slow time scale like a turbulent process. And it's not quite weak turbulence because you don't have dispersion in K space, so you don't have to go to higher order statistics to get the closure of the theory. You can stop right at the order epsilon in your expansion. Essentially, the theory you get is that the distribution function, the slow part of the distribution function, evolves by this kind of interaction with some sort of effective potential. And the effective potential is determined by a resonance condition where you have a window in velocity space. So if you consider a velocity space you consider G at this velocity space point here, the waves a little bit further away from this point, left and right, are going to have frequencies which are very similar, and so you'll have approximate resonances for those frequencies. And then when you get outside of the window of this resonance, the contributions are no longer there. So that's a general idea of it, and that you can derive this sort of scaling law, which is consistent with this picture. And it's a highly anisotropic process, but anyways, if you average over the angle and look at K perp, you get a power law, which is K to the minus 5. So it's just very preliminary results, also from Tomo, which is, we've basically taken one of his perpendicular cascade simulations that he's already done, and we've run it until some time step t equals 9. We've allowed the cascade to sort of develop and produce this 10 to the minus thirds, k to the minus 10 thirds that we expect. And then at that point we switch on this phase mixing process and see what happens. And the spectrum steepens a bit, and I mean, this is sort of something that is observed for a small period of time, but it's not clear that this is an asymptotic state or anything, but it's just encouraging that maybe this idea could lead somewhere. Okay, so that's it for that part of the talk, for our results. I wanted to show these plots and just sort of open it up to discussion. What we have here are some...
Maybe before you start talking about ITG.
Yeah.
This is a question about inverse cascade.
Okay.
Some years ago, and my memory is totally foggy, maybe somebody can remind me, there were high K simulations of forced, either it was Hasegawa-Mima or Rossby wave turbulence, the final state of which was a crystallization. Can anybody does anybody remember this?
Oh yeah, the Chetkov and company.
Yes, exactly.
It wasn't the first one.
Yeah, you're right. Anyway, so of course the crystallization is interesting. And does your inverse cascade at high K perp here have anything to do with what they were doing in their simulations? I mean, they were doing fluid phase, I believe, and you're not.
Mm-hmm.
They were in the low wavelengths.
They were in the high K perp rho S level, bigger than 1.
He said rho I.
Yeah, but
Rho I less than 1.
was small, right?
I don't think they had a concept of rho I.
Okay.
Well, that meant they were in the Navier-Stokes limit rather than potential limit, basically, right?
Right.
So they were basically simulating the two-dimensional Navier-Stokes equation, possibly with a d phi by dy term in it somewhere.
But I just can't remember the details. I just wondered whether
Right.
there was any contract that you had thought about, or whether it's totally irrelevant.
But everything he's doing is at sub-Larmor scales, which...
Well, I think that's what they were doing.
No. They were doing sub-rho s, but above rho I.
Okay.
So
Well,
there was
we'll-
no gyro averaging. It was just this,
Well, we'll have
it's
to
just
look.
the sound physics was in there, but not the...
Oh, that's true. I guess probably.
It was cold ions, right?
Maybe. Yeah. All right. Probably. Okay. No contact.
All right, so Alejandro Benyon Navarro and Daniel Karate and some other workers in Brussels have been using Gene to look at this sort of entropy balance, but they have in mind the goal of trying to develop subgrid scale models. So they're very interested in how local the interactions are in K-space and diagnosing these things in an ITG simulation. So this is sort of a typical cyclone-based case. It's not very well resolved in VPerp, which is, sort of state of affairs, I suppose. And actually the dissipation here is only in the parallel direction. So it really relies on this
I mean, it's a parallel viscosity.
there's a parallel hyperviscosity and
Parallel hyperviscosity.
yeah, NV parallel and K parallel. So this is sort of what you, I mean, this is not unexpected. This is sort of what you expect. We know that the transport happens up here, and therefore injection rate happens up here. This is what we understand. This is a K by K look at it, which is interesting. So some things to point out about what they're seeing here. The injection happens at K less than 1. This scale is a little confusing because it's logarithmic binning, and there's also some deviation from that, the low and the high Ks. But essentially, 10 is K rho of 1. And they claim to see some sort of self-similar behavior of the cascade between 1 and 4, K rho of 1 and 4. And I'm not completely sure exactly what's meant by that, but the claim is that the transfer function only depends on the difference between L and L parallel L prime in that region. So that's what they're observing. It's clear that dissipation occurs throughout this range. There's no clear inertial range in the formal sense. However, if you integrate this curve, this basically comprises all the injections. That means that up to this point, the flux of free energy in this cascade is going to be maximal, and it's going to start to decay. So if you want to really determine whether there's an inertial range here, you should really be comparing the flux with the dissipation rate. And but it still remains that the dissipation is finite throughout this range and sort of steadily growing. And this is due to the K bending. It's not a physical effect. So yes, local, forward, and stationary, which is important, as we all know. It's important to verify that these simulations are stationary, that there's a balance between the injection and the dissipation with respect to free energy. Yeah.
Can you quantify that zero? I mean, how well does this conserve free energy?
Right. No, I don't know. We can look through the paper, poke through it. There's a draft of the paper. So I'm not sure exactly. I mean, it's not my work, but yeah, we can look into that. We can also ask them, get them on Skype later with Tomo. All right. So another thing, it's not really showing up very well. This looks very light here. That's too bad, because it's kind of interesting. But here's a look at this other quantity, the energy quantity, the electrostatic quantity here. So one thing to note is that the dissipation across here is sort of 1 part in 10,000 of the dissipation for the free energy. So it's actually very, very close to 0, and this quantity is not being dissipated at all collisionally. But this may be just that they have not reached steady state, because the injection is still positive here. So the total injection of this quantity is still positive. Anyways, putting those issues sort of aside, if we look at the transfer function, this bit here is blue. Sorry, that's red. And there's some red up here. So it's kind of interesting. There's a sort of a recirculation of this quantity in K space. And at the fine scales, it corresponds to a local inverse cascade. And at the large scales, there's a non-local forward cascade. So there's sort of cycling of energy in this simulation. And I thought that was pretty interesting, especially if we want to think of this quantity as sort of diagnosing how two-dimensional the system is. Then this is an interesting result to look at. So how am I doing on time? Basically out of time here. Yeah.
We didn't get to the small scale.
Right. So this is also a reason to think since this quantity is not being dissipated in this case, another reason to think it sort of looks two-dimensional, that the energy quantity is not being dissipated down here where the dissipation is strongest.
So you're just finding up energy at large.
Large scale energy sort of piling up. That's right. I don't have a good intuition for this, but I don't know if people, obviously people look at the potential. I don't know if people look at this quantity in particular and see if, and look for convergence of their simulations in terms of this quantity. But this is maybe something to think about in general. So I've had a little time to look at these and think about that, and those are my general comments. But we can continue to look at this and think about it. If there's any comments now, can voice those as well. That's pretty much the end of my talk. Well, I mean, these results are not. Again, we emphasize they don't really treat the perpendicular cascade in the way that we've been treating it. So there's no dissipation K-perp space. There's no dissipation V-perp space. There's no collision operator here. It's really sort of an artificial way of damping the system. But taking them for face value, they don't really, don't really have much of an inertial range behavior here. But in any case, you have highly local transfer, and the direction of the transfer is toward the small scale. So it's very sort of consistent with this idea from fluid turbulence. This is how we expect the energy quantity to behave, cascading to small scales. And they're very encouraged by this for the purposes of developing the large eddy simulations, subgrid models, because they believe this implies they can consistently take the small scales to be acting as a damping, effective damping of the system. So that'll be it for me.